Good day, friends. My name is Odo Emmanuel from InsideSkills.com, and today we're going to be starting up our machine learning series. And I'm going to starting first with linear regression. And today we're going to be looking at linear regression in depth. So, without wasting much time, what is linear regression? Linear regression in statistics basically is a linear approach to modeling the relationship between a scalar response and one or more explanatory variables, also known as the independent and dependent variables. Regression algorithm are a type of supervised algorithm that basically uses features of the input data. These are data that are being passed into the model to predict a value such as maybe the cost of a house, maybe the cost of a stock prediction, site. It can be used to get specific features like the size of the house, the age of the property, the number of bathrooms, the number of bedrooms, the number of stores, the space per square meters, the number of floors, and so many other features. Specifically the location of where the property is. So these are just to mention but a few what you can use linear regression to achieve. In linear regression algorithm, the goal is to minimize a cost function by finding the appropriate parameters of the function over the input data that best approximates the target values. A cost function is a function of the error, that is, how far we are from getting a correct result. So for a simple linear regression, your y is your dependent variable. Why you have one independent variable, which is your x-axis, and you have the beta, which is your slope. Then the alpha is your y-intercept. So this is just a simple linear regression formula. So here is a simple linear regression graph that has been plotted. Here on the y-axis, we can see the parameters there, which is called the dependent variables, while on the x-axis, which is below, is your independent variables or matrix of features. Then the red line that is crossed here is your slope, while the dotted line is the data that has been fed into the data that has been plotted. So the dependent variable y needs to be predicted, while the independent variable is used to predict the dependent variable y to minimize the error. So basically, when designing a linear regression, it's not just for you to copy the formulas. You need to understand what the business requirement is before you're plotting. And you need to do your specific research, not just to follow some of the things I say. You need to do your research. Part of the things you need to work on is knowing linear regression has the following assumptions. One, weak exogeneity. This essentially means that the predictor variable of x can be treated as fixed values rather than random variables. Then no or little multicollinearity. Multicollinearity in this case, in which independent variables are correlated with each other, and this situation creates unstable models by inflating the magnitude of the coefficients / the estimates. It also becomes difficult to determine which variable is contributing to to predict the response variable. Then for linearity, this means that the mean of the response variable is a linear combination of the parameters and the predictor variables. Then for independence of error, this assumes that the error of the response variable are uncorrelated with each other. Errors should be almost stochastic. Errors should have constant variance with respect to the independent variable, which leads to more practically wild or narrow confidence intervals for estimates, which degrades the model's performance. One reason for not holding almost stochasticity is due to the presence of outliers in the data. So you can just read more and understand what some of these things is, because this focus today is not on this. Our focus is we're just highlighting them. So there are specific things you need to understand before you draw the model, and these are just statistical terms. You have your mean square error of an estimator, which measures the average of the squares of the errors. The average square difference, the estimated value, squared error coefficient of definition. This is the measure of the percentage of the response variation that is explained by a model. It is also a measure of how well the model minimizes error compared with just utilizing the mean as an estimate. Then your coefficient is just a factor that describes the relationship with an unknown variable. So here's the code has been plotted. This is just a simple linear regression. And you can see the black dot here are the models. They are the models that we've been able to model using the data from y variable with x variable. So we've plotted this graph, and this blue line that cuts across it is our trend line. It shows this is a linear line. It means this is a linear variable. So it has predicted. See that the predictions are mostly close, to the predictions. So this is the code, and we'll work around it now. So we import matplots leave as matplot leave put by plot as built-in. Import the numpy as np from scalar. Import our data set that we're going to be using in a linear model library or class from scalar. Import so from scalar we import mean square from scalar dot matrix we import mean square error, then error to underscore. So the first thing to do is to load all our models, all our libraries. We've imported all our libraries. As you can see, all our libraries have been imported. So here we'll now start the main code. So we import x variable, variable x, variable y, is equals to dataset dot load diacritics. And we're returning these parameters to x, y, true. Because we're loading this from sklearn library. So we can even print the x variables. Let's even see what's inside. So x variable y. So I have the data here. So these are x variable and these are the y variable. Let's see x variable x. Just want to call our feature. So we're going to split our data into training and split sets. Variable.xtrain. So we'll start with our x variables first. Say variable x. Yeah, we're going to slice them. Next text. So same thing. Do the same thing for our y variable. So yeah, we successfully splitted our variable to x train, y train. Now it's time for us to bring in our regression model. So can as well pass it to this parameter as linear dot in regression. Now we need to fit it in to have to call this fit. So passing our two variables x train and y train. Yeah, we'll predict our model calling the y pred. Square pred is equals to right dot predict. Here we'll pass in s test variable. So we can print out the coefficient. Coefficient. We'll print mean squared error. two floating values. Don't know y variable. Right, bread. Find coefficient of determination. Two floating points. Only have to score function. My tests. Variable by test. So here we'll print a scattered plot. Two dots scatter. Print our X text against our Y bread against our Y tests. Dots plot. X test. PLT dot S. That X 6. Now we have the PLT dot show. This variable here. So now we run Sorry, I saw this typo here. It's supposed to be the x variable train, and here I didn't have the color, so I just saw the errors now. Color default to blue. So So let's run our model and see the outcome of it. There was another typo error here. I just changed it to x variable. I didn't see that, so I just saw it now, and then when I ran the model, this was what we got. Yeah, the coefficient is this. Our mean square error is this. The coefficient of determination is 0.4, which is not bad. So again, let's run it on the final time. So this is our map, our linear regression, which is a straight line. So that with that, we come to the end of this video. Please subscribe and like our channel. Thank you very much.